Am I on? All right. I think I understand the tech. Let me make this a slideshow. All right, so in this video, we're going to look at, I'm going to introduce infrared spectroscopy, sort of theory and what you need to know. Okay, so again, you're going to find this information in chapter 14 in Klein. And as I said in the last video, I thought these moved. Oh well. Infrared spectroscopy is going to tell us what functional groups are present. And the reason it does this is the physical transition in a molecule that happens when an infrared photon is absorbed is a change in vibrational state. All right, so any two atoms are always vibrating, like two balls on a string. Okay, molecules have energy. And in fact, that's what we feel is heat, right? So molecules are zipping around the room, and molecules are vibrating, and the hotter they get, the more they vibrate. So we've got just a simple stretching vibration, and that's the simplest thing to look at. And primarily what we're going to look at, what we're going to focus on in iron spectroscopy are these stretches. We've also got these vibrational states. Those are a lot more complex, right? So depending on what the three atoms are, like a CH bond pretty much vibrates like a CH bond. I mean, it changes a little bit so we can learn something, but they're all right in the same basic area of the spectrum. These vibrational states can be wildly different. So we're going to focus on this. And like I said, infrared spectroscopy is going to tell you information about functional groups. How does it do that? One of the things I like to do with PowerPoint lectures, if you ever have me in the classroom, I like to draw on the board, and my brain will keep up with what's on the board. I like to get ahead when I talk of the slides. So when you record an infrared spectrum, you put a sample in the spectrometer, you bombard it with infrared light, and on the other side you have a chip that records what light gets through. And so what you're really measuring is which frequencies or wavelengths of infrared light are absorbed by the sample. And that's going to tell us which functional groups are present. All right, so here is an infrared spectrum. This is what you will see as an infrared spectrum. Pretty much every spectrum you ever see will look something like this. All right, you're going to have absorbance versus energy. So there'll be some, is that on the screen? Looks like it's on the screen. Right, so energy on the x-axis, absorbance of some sort on the y-axis. In an infrared spectrum, we do percent transmittance. That's helpfully right on the line. This is percent transmittance. So 100% transmittance means none of that wavelength gets through. 0%, let me back up. 100% transmittance means all of that wavelength gets through. 0% transmittance means none of that energy gets through. And as you can see, we've got bands. So we call this an absorbance band. That'd be an absorbance band. Here's some absorbance bands. And this would be strong, right? Because it's really absorbed. Like it's down here like 15%. So something like 85, 90% of the wavelength that here is absorbed by the sample. And these little things up here would be called weak, right? There's an absorbance band there, but not much. So that's the absorbance axis. The energy axis is given in wave number or reciprocal centimeters. And that's not going to be something that jumps out at you right now as an energy. Okay, but a wave number all right, so the wave number is equal to the frequency of the photon divided by the speed of light. Something physicists came up with in the early 20th century, and we've stuck with it. Your typical infrared spectrum is going to give you 4,000 wave numbers down to 400 wave numbers. All right, it's a frequency, right? So the wave number is a frequency measure, and so the larger the number, the higher the energy. So high energy is down to the left. Low energies to the right. So we've got, and again, in all spectra, you're going to measure the strength of the absorbance versus energy, right? At 210 nanometers, you have a strong absorbance. At 504 nanometers, you have a weak absorbance. At 5 microns, you have a strong absorbance. At 10 gigahertz, you have a weak absorbance, something like that, right? All right, so this spectrum would tell us what functional groups are present. You're going to have some information. I don't know what Dr. Lukesh and Dr. Welker are going to require by the end of the semester in the lecture. I will always give you kind of a table of information. We'll talk more about that in class. So you're not going to have to memorize a ton, but you're going to have to learn how to use the data. All right, so you'll want to sort of put some things in mind. Yeah, this one is it's the same spectrum, and it's telling you what I just told you. You want to characterize an absorbance band by wave number, intensity, and shape. So like this one is broad. This one would be sharp, right? So how wide is that band? And here's some math that you don't really need to get into. I'm not gonna ask you to solve these equations. This is just sort of explaining some of it. All right, so the frequency for a stretching vibration is going to depend on how strong the bond is. Again, it's a stretching vibration. Put a stronger spring in there, it takes more energy to make it stretch. It also depends on the masses. And again, you know this. If I've got 2 balls on a spring and they're really light, right, they're going to bounce all over the place. If they're both really heavy, they'll just sit there. So the bigger the mass difference in the 2 atoms, or the bigger the masses, it takes more energy to make them stretch, and the stronger the bond, the more energy it takes to make them stretch. So again, stronger bond, bigger mass difference, more to the left, to the higher energy part of the spectrum. All right, so remember, our spectrum in an IR is 4,000 wave numbers down to about 400 wave numbers. All right, and if you look at this, so let's take strong bonds first. So down here on the bottom, I've got a carbon-nitrogen triple bond, carbon-nitrogen double bond, and carbon-nitrogen single bond. Triple bond's obviously going to be stronger, right? There are 3 bonds there. So it takes more energy to make the carbon-nitrogen triple bond stretch, 2,200 wave numbers. The double bond is at 1,600. The single bond at 1,100, right? So the stronger the bond, the more energy we need. And then, and this comes out of the physics as well, that the bigger the mass difference between the 2 atoms, the more energy is needed to make them stretch. So a CH bond comes at 3,000 wave numbers, and this is an atomic symbol you might not be aware of. Deuterium is the heavy isotope of hydrogen. All right, so D is just a hydrogen atom that's got a neutron in the nucleus. All right, so CH, right, H weighs 1, 3,000 wave numbers. The CD, the D weighs 2, so it's twice as heavy as the H, 2,200 wave numbers. The CO bond, 1,100. Right, so C and O are roughly the same mass, very little mass difference, and they're both much heavier than a hydrogen, so way less energy getting them going. Carbon chlorine, now there's a pretty big mass difference, but both atoms are also heavy, so it doesn't take much energy to get that going. All right. So, really important. This is like tremendously important. You want to have this more or less in your brain. Not now, not today, not at the beginning of lab on Monday, not even at the end of lab on Monday. But this is where you're headed. You want to be able to look at an infrared spectrum. Again, 4,000 to 400 wave numbers. Right? 4,000 to 400. And sort of place what is where. So bonds to hydrogen, 2,700 to 4,000. Again, big mass difference. So those are all way down on the left. Higher energy. So I should put that. Right, higher energy is on the left. So that XH, anything, CON, whatever. 2,100 to 2,300, you've got triple bonds, stronger bonds. And this is really important. This is a really important one. Carbon-carbon, carbon-nitrogen, carbon-oxygen double bonds, 1,600 to 1,850 or so, and then single bonds. Down here, single bonds aren't all that helpful. Why aren't single bonds helpful? Well, every molecule's got single bonds. Single bonds have to be there to connect things. If you want to learn about the functional groups, you want to look at these. Right? One other thing that's not on here, you write it. And again, this falls out of the physics, which is really cool. So there's two classes at WIG that you might take, Chem 334 and Chem 342. I think it's called Instrumental Analysis and Physical Chemistry 2, where this is looked at, all the physics I'm sort of glossing over and just telling you to memorize. This is where they are, and it's really cool, all right? The interaction of light with matter is a fascinating subject and one we don't really fully understand. We've learned a lot just in my lifetime. We'll learn a lot in yours, maybe you can help with that. So right now in this class, you just kind of have to commit some stuff to memory. But if you're interested in like diving deeper on it, those are the two classes you do. All right, stronger bond dipoles. The bigger the dipole in a bond, the stronger the absorbance in the infrared spectrum. So for example, you might wonder, how do we tell a carbon-oxygen double bond from a carbon-carbon double bond, right? You're going to have the same basic frequency of absorption. But you would have here, right, that would be the CO, and then you might see that would be the CC, right? Really weak absorbance for the CC, really strong absorbance for the CO. And the reason is, CO's got a strong dipole. And in fact, if you had a symmetric carbon-carbon, like if you had ethylene, there is zero dipole in this carbon-carbon double bond, right? CH2, CH2, no dipole. This does not absorb IR light, which is, I think, really cool. Okay, so let's go a little bit deeper. That's basically the same thing. We call this the fingerprint region. There are single bonds and bending down here, right? All those single bonds and the bending, it's complex, it's chaotic, and it doesn't really tell you much. So ignore this. Ignore that region, basically, is what I'm telling you. However, the fingerprint region can be like, you guys have all seen CSI, right? So you kind of might have an idea what I mean, or what is meant by the fingerprint region. So here's two alcohols. Remember, I said that IR spectroscopy is supposed to tell you about functional groups. Both of these have an alcohol functional group. Might not surprise you that that is an OH. That's the OH stretch right there. These are CH stretches. Right, again, CH, pretty much every organic molecule's got a CH stretch. So it doesn't tell you much. But OH tells you there's an alcohol there. But then look at the fingerprint regions. These are really two very, very similar molecules. And yet, the fingerprint regions are wildly different. If you look just to the left of the fingerprint region, right, 1500 to 4000, they look basically the same. Except I've written over them so you can't see that. Right? This region and that region look essentially the same, and you would expect that from two really similar molecules. But then you get down to the fingerprint region, and they look very different. So, if you had, like let's say you had a catalog of spectra, and you had an unknown that you thought might be one of these two, well, this region's not going to tell you much. Okay, it's an alcohol. It'll narrow down that you want to look at the alcohols, and it's got CH bonds. There's no double bond stuff. These are too weak really to be double bonds, so there's no double bond stretches. So you go into your catalog and you find a fingerprint region that matches, like a fingerprint in a crime scene. All right, so again, the diagnostic region of the IR is above 1500 wave numbers. 1600 to 1850 is going to be double bonds. 21 to 23 is going to be triple bonds. 2700 to 4000 is going to be bonds to H. And you're going to want to look at wave number, intensity, and the shape of each signal. Right. Another really cool thing, and this again, I've got this committed to memory because I've done this a long time. It'll take you guys some time. In that region where it's XH, so bonds to hydrogen, OH is going to come farthest to the left and be strongest. NHs kind of come between OH and CH, and you'd expect that based on mass in the periodic table, right? N sits between C and O. And then the CHs can also be divided, and this is the weird kind of cool thing. So to the right of 3000 are going to be sp3 carbons bonded to hydrogens. To the left of 3000 is going to be sp2 and sp carbons bonded to hydrogen. And that 3000, it's an easy number to remember, and it is pretty ironclad, which is weird, I think. I mean, it's completely coincidental. It doesn't mean anything. It's just that 3000 is easy to remember. To the right of 3000 is sp3 CHs, and to the left of 3000 is sp2 and sp CHs. And these are going to be weaker. Right? So very often you might see this, well, let's actually look at some spectra. How about that? All right, so again, just putting up this thing you need to know. I'm going to keep harping on this. NH, OH, CH, 2700 to 4000, down on the higher frequency end of the spectrum, triple bonds, double bonds, fingerprint region that you can ignore. Okay, so you can't solve an entire molecule from an IR spectrum. If I give you an IR spectrum, there's no way to know exactly what the entire molecule is, unless you have a catalog and you can go to the fingerprint region. What you can do is get functional groups, all right? And so, again, we've got XH bonds, and then in the middle, we've got double bonds. So probably the first place to start, the first stretch to learn is the CO double bond. Right. The CO double bond is going to be strong, and it's going to be, if you see the entire spectrum, it's going to be basically right in the middle of the spectrum. Right? So if you get this really big, kind of not super broad, but a little broad peak right in the middle, it'll tell you you've got a carbonyl. A CO double bond is a carbonyl, and it's in a variety of functional groups. And then down here we've got a whole bunch of CHs, right? Fairly uninteresting. Organic molecules are going to have CHs. And then ask yourself, is this an alcohol? All right. It is not an alcohol. An alcohol has an OH, but that OH can't be bonded to a carbonyl. And there are reasons for resonance. For one, the electron withdrawing nature of a carbonyl. When a carbonyl is bonded to an OH, this is a carboxylic acid. It's a functional group you definitely need to know. It's a really common one. That H is quite acidic, based on what you'd expect from the name. And the reason is, right, if I pull this H off, I get an O minus here, and that O minus can be delocalized over the two oxygens. Anyway, carboxylic acids, which you'll see written as CO2H, have super broad, strong peak band. All right? And you might say, well, you know, if this absorbance here, it's not as strong as the CH. But look, we've got 7 CH bonds. We only have 1 OH, and the OH is nearly as strong, right? So it's additive. If you have hundreds and hundreds of CH bonds, you're going to have a really strong CH stretch. But any one CH is pretty weak. 1 OH is usually going to get you quite a ways down the page. And that's basically all you get out of this molecule. We got some CH, we got a carbonyl, we got a carboxylic acid OH, and we have a carbon-oxygen double bond. Can I hopefully put that? I'll put all these PowerPoints online as well, just by themselves. All right, so let's look at this one. And again, look at that. That didn't change any. Here's the molecule down there. We no longer have a carboxylic acid. We've put a methyl in place of that H, and that changes things considerably. This is now called an ester. All right. Again, carbon, oxygen, carbon is an ether, unless one of those carbons is a carbonyl, and then it changes the electronics. So we've got an ester. We don't have any OH. See, if you go back, watch the spectrum. Go back. You got an OH. The OH goes away. The carbonyl in the ester stays basically in the same spot, right? Big strong peak right in the middle. That's a carbonyl. If you don't remember any IR besides that, you'll be all right. I shouldn't say you'll be all right, but you'll know something. All right. This molecule does have CHs. Now you see how weak the CHs really are. We have one carbonyl. We have 8 CHs. Here's our 8 CHs. There's the one carbonyl. Massive difference in absorbance. And if you took this straight up, 3,000 hits right there. So they're all sp3 CHs. And I've put this, that is a CO single bond. Don't worry about it. You don't need to use that or know about it. Right, so again, now we've got a molecule. We don't have a carbonyl. Functional groups. Hit pause and think about what the functional groups are. Okay, you're back. First of all, we don't have a carbonyl, right? These are too weak to be a carbonyl. What we have is an ether and an alcohol. Right. There's the OH, and we've got CH again, basically in that same spot. All right, so I think you start to see what we're doing here. We're just finding functional groups. All right, so if we go back here, now we have carbon, carbonyl, carbon. That's a ketone. Like I said, there are a bunch of these carbonyl-containing functional groups. So we have a ketone, a carbonyl, and an alcohol. sp3COH. So again, this molecule has CH bonds. It's got an OH, but it's an alcohol OH, so it's not super broad, right? The carboxylic acid, you'll remember, sort of did that. The OH is actually deeper but narrower. The alcohol OH. And then you've got CH, carbonyl, and CO. So really, you're going to be able to identify functional groups that are present. And as you'll see in the next video, you'll be able to use this in a process of elimination. So if you have a set of compounds that might be your unknown, and you take an IR, you can eliminate them based on functional groups, right? Whatever molecule I come up, I couldn't come up with this molecule exactly from this spectrum. But I can tell you it's got to have an alcohol, there's got to be some sp3CHs, there's got to be a carbonyl. Any molecule that doesn't have one of those three things is not it. All right, we'll see that on the next one.